Very happy to be here talking about bridges and a little special secret method at the end. So who here has already used a bridge in crypto?
Has used?
Yeah, used. Okay, who's tried to like build a bridge in some way? Oh wow, we've got a few people. So have you got ideas as to how you can build a bridge? Basically, you've got two different blockchains. As you all know, they are kind of independent. You cannot make them easily communicate, right? Because the point of a blockchain is that it's really deterministic. You cannot be here and do HTTP requests to the rest of the internet. It would break consensus. So how do you do if you have, let's say, Ethereum? On the other side, you've got another blockchain like, okay, Solana or Near. Let's take Near as an example. And you want to bridge Ethereum to Near. Does anybody have an idea of a method to do this?
How to do this?
Yes.
I think the pattern actually is very common. That's log from the source chain. That's log user log token into a smart contract, and there will be a message to emit.
Okay, exactly.
Then actually there will be all offline relayers to listen for the message, and they have the privilege to mint the token on the targeted chain. I think the pattern is very common like this.
Okay, so that's a good point. Most of the time you will lock tokens on one chain, and then there will be a relayer or something passing the message, and then you'll be able to mint it on the other chain. So that's like what happens most of the time. Actually, we've got multiple ways of doing it, and basically we've got three different ways that are often considered as the trilemma of interoperability or bridges. And those three ways have different security trade-off and different kinds of trade-offs. So basically, we can try to build this. We can try to like draw this triangle with like three different things, and basically we'll see like three methods. Thank you. We'll see like three different methods to bridge, and you'll see basically their trade-offs. So an extensible here. Okay. So the first method that was experimented a lot, very much at the start of like blockchains, for instance, there were like the first bridges between Bitcoin and Litecoin, are HTLCs, or hashed time-locked contract, or atomic lock. Those are basically all the same things. And basically the idea is that, okay, let's say you want to bridge like like let's say you want to exchange, okay, it's not like, later it was not done for bridges, but let's take a simpler example in which you want to trade Bitcoin for Litecoin. You will be able to like have someone lock some Bitcoin on one side, then someone else can lock some Litecoin on the other side, and then with a signature from the guy who locked Bitcoin that says, okay, I accept your offer, the person who wants to buy the Bitcoin can withdraw it, and with the new signature he has to do, the person that wants to sell the Bitcoin can now buy the Litecoin. So this is like the HTLC basically design, atomic locks, which is here. So let's put atomic locks here. Then between generalizable and trustless, you've got light clients. I'm going to explain what it is in just a few seconds. Yeah.
You have one person on the Bitcoin chain who wants to bridge to Litecoin, and there's another person on Litecoin who wants to bridge to Bitcoin.
Yeah. So this is not really for like this was used later for bridging. I was just explaining a simple example, more like for trading. In a trustless way, but I'll explain more later, like the basically the trade-off space between all of this. And then you've got like MPC or TSS. So basically, if you want to do a bridge between like Ethereum and Solana to be able to have wrapped Ether on Solana, the easiest way to do it, and the way it's done most of the times, is by having a kind of multisig or a kind of validator network that basically votes whenever you lock some Ether here and meets it on the other side. So basically, the idea is that you're going to have a bridge contract here. You are able to lock some Ether, and then you've got a relayer network or a validator network that will listen to all of this. So let's put relayer here. And then he will allow you to mint on the bridge contract on this side, wrapped Ether. So now the question is, and that's the whole point of bridging and of all of those trade-off, what decides, right? Because you've got no good Oracle system. It's just like Chainlink. You have to have a way to know. So most of the times how it's done today is through MPC or TSS, so threshold signatures, multi-party computation, or just basically multisigs, or like node networks that rely on the majority trust assumption that basically just vote in most ways. And okay, it's safe if you trust the nodes, but it's actually not the best system because it's not trustless, right? That's why it's not on the trustless side. Atomic locks would be basically, okay, I've got a token here, I've got a token here. You can actually, if you have smart contracts on both sides, you can actually lock them, and then with a signature from one person, deblock it, get the tokens on the other side, and with the signature of the other person, get the tokens on the other side. So this is trustless, and it's extensible. That means that it can be rapidly and easily deployed on new chains. But the problem is that, first, it's quite cumbersome because you have multiple steps in the process. You cannot just do it in one step, like bridge in 1 second. You have to have a kind of marketplace or something that would be peer-to-peer in which people put offers. And the other problem is that you can only trade cross-chain tokens that already exist on both sides. So it doesn't really work for a mint and burn mechanism. For a mint and burn mechanism, you have to have one of these two. You cannot mint new tokens in this way, and that's why I was starting with the like Bitcoin and Litecoin example, because it's actually not a good example for this example in which you have to create new wrap token, right? To create them, you have to have a contract that mints them. It's only good, for instance, if you already have this and then you want to create a marketplace, you can use atomic lock because they already exist on both sides.
How does it work? So you lock contracts in one chain and someone else locks tokens in the other chain?
Yeah, so
you will send a signature that using which the other guy can claim on the first chain, or how does it work? How is it atomic?
okay, so let's say I'm on Ethereum, so this bridge already exists, and now we are going to use another like atomic lock bridge here. Okay,
Yeah.
let's say it's a kind of marketplace. So I've got Ethers, and I want some wrapped Ethers, let's say, or we could even do it for just Sol or whatever. And you have some Sol, let's say it's Sol, and you want some Ether. So basically, I will lock my Ethers in a contract, and I will go on a marketplace like off-chain on a website and say, oh, I want to sell 1 Ether for 10 Sol. You will also lock your Sols in a contract. And basically, so let's see. The way it works is that if I accept the lock you did on this side, I'm like, oh, okay. So I'll do a signature that allows you to withdraw my Ethers, okay? But on one condition, that you also do a signature that allows me to withdraw those. So if you do a signature that does not allow me to withdraw those, I'm just not going to sign and allow you to take them here. But if you do one, I'm like, okay, you can take mine, I can sign, but then I'm going to take those. And of course, here in the contract, it also verifies that I did the right signature here.
This one verifies that you take the right signature.
So this one verified. Okay, let me see. So like I lock, you lock, and then you can take those if I make a signature that I accept this one, yes. And then when you take those, you publish a signature to be able to take this. And the signature you published, if I put it here, I can take those, basically. It's quite cumbersome. There is 4 steps at minimum. If you count the off-chain steps, like putting an offer on a marketplace, it's 6 steps. It's not that not that good, and it doesn't really solve the mint and burn problem. So it's kind of like another design. But basically, the two main design that allow you to mint and burn are MPC or TSS designs, in which basically you trust a kind of majority assumption, and light clients. Light clients are really interesting. They are kind of the end game of bridges, and they are kind of the perfect design. The problem is that they are really, really hard to do. And basically, the way a light client works is that on this chain, I'm going to verify the whole consensus of Ethereum. And on Ethereum, I'm going to verify the whole consensus of Solana. And this way, I'm going to be basically perfectly sure if it works really well. There is no additional trust assumption. Like here, I'm going to be sure, okay, someone burned wrapped Ether on Solana, so I can unlock it here. And here, I'm going to be sure someone locked some Ether here, so I'm going to be able to mint some wrapped Ether. So basically, the idea of a light client, you all know about light clients, like standard one that you can basically use on your computer, like a light client node. It will not compute all of the transactions. Basically, it will just listen to the block headers from other chains, from the other nodes. Then it will verify that transactions are included in this in the tree. It's really light compared to having a full node. And if you are on Turing complete blockchains, you can actually run a light client. It's just really hard to do. You have to implement something that's very, very big. It's going to cost a lot of gas. For instance, with the Ethereum 2.0 consensus, it's quite complex because you've got validators, you've got rotation of validators, you've got rules with all of this, and so it's quite cumbersome. There have actually been some teams working on doing all of this with ZK for the succinctness part, not for privacy, of course, but for succinctness. So basically, the only times that Ethereum consensus has really been implemented in this way are by the Rainbow Bridge team between Ethereum and Near. So they already did it back when it was a proof of work. They redid it by when it's now that it's proof of stake. And basically, the way it works to bridge between Ethereum and Near, it's one of the only chains that actually work like that. So it's cool that they actually made this effort. It's some of the guys that also did 1inch, very, very impressive team. So basically, on one side, when you want to do this, Near, it's actually pretty cheap in terms of gas. So you can implement a whole Ethereum light node, and it will be the case. And so basically, they implement it. And on the other side, do they actually verify the whole Near consensus? I'm not sure about that. I think either they have another system, like some kind of trusted system or some kind of optimistic system. I'm not sure, because it would cost a lot to verify the Near consensus on Ethereum. And the two other teams that have been working on it are from Succent Labs, like Uma Roy and her team. They've been doing telepathy, which is basically an Ethereum consensus bridge. They did it between Gnosis and Ethereum, and it's all in a circuit, and it's a lot of constraints, millions and millions, tens of millions for each block, and so it's really hard to operate. And also the team from Polyhedra that now works with Layer 0 Labs. Okay, so basically, I don't know if I was clear enough. Tell me if there are anything. But basically, the main point of what I'm trying to explain is that, okay, let's just summarize this in 2 sentences. Now, 99% of bridges are here, and you basically trust the people. Either it's a big multisig, either it's a node, like a little node network, but basically you trust them. The end game, the most impressive thing and most incredible and most reliable would be to verify the consensus of all the chains on the other chains. The problem of doing that is that you have on each chain to actually implement a whole node. It's quite complex, and also it doesn't scale well because let's say you want to add a new chain to the bridge. Well, when AnySwap or multi-chain bridge that got hacked a few months ago tries to do that, it's so easy. They just add things to their code with the multisig. It's quite easy. Now, if you want to do light reliance, you have combinatorial explosion. You want each time you have on each chain to verify the consensus and of the other chain. So it's quite messy. Okay, so now we're going to look at.
I have one question first. So when you say that you have to verify the consensus of one chain on the other, like for example, let's take Ethereum proof of stake, and what are the steps involved? Like what?
Okay. Very good question. Let's do that let's do that quite fast. So basically, okay, I come here and I'm locking Ether on the bridge contract.
You do a transaction or something.
Yeah, I'm doing a transaction. Now the big question, the $1 million question is, how do I know on here that I can mint some WOTH? You shouldn't allow anybody to do it. So either you basically rely on new majority trust assumptions, or either you verify the actual Ethereum consensus. And the way you would do that is to run a light node and bring all of the new blocks. And then in a new block, you've got the state root, like the block root, then it's Merkleized, you can get the state root, and then inside you can see that there was actually a consensus, there were a transaction that was validated here, and that actually included your lock. And so you can mint the wrapped Ether. So the big question is security here. Is the light client good enough? Is it like running properly? Because if it's not, you can forge arbitrary transactions.
And for this, do you need like the block hash or something of the source chain, or do you just need, or do you not need it? Like, do you need any extra information, or?
Yeah, you need the block hash from the source chain to be able to prove that the transaction was included. If you don't have it, you cannot prove that it was included. That's the point of running the whole light client. If you don't do it, you cannot know for sure. Or you have to use Chainlink, but we all know, okay, this is filmed, but we all know Chainlink is a big multisig, so it's kind of the same as doing this. Okay?
There is no like trusted kind of setup, not setup, but like trusted step happening here. Like everything is trusted in this. If you create this proof of, I know, some transaction was there in this block in the source chain, and you prove that it was validated by all the validators or something, that's it.
That's it. That's the magic of light clients. That's why they are so good, and they are like considered by everybody as the perfect bridges in some way, but they are so hard to do. Is that, it's a big technical challenge, and as I said before, you have to do them on all of the different chains you want to support.
What do you call the light client? Is it, for example, like implement a Rust light client, or is it a smart contract that's actually?
Well, basically, most light clients right now, they are used like in Rust, for instance, but you have to do one in Solidity or in Near. I think they use Rust, if I'm not mistaken. So it would here be in Rust, but in the smart contract framework that Rust uses.
Yes, because basically, if you want to access like mint functions or anything like that, you need to be the execution layer.
Yeah.
You need to be able to have actually a smart contract that listens to potential like blocks on the other side. For example, if you want to mint a near, means that you need to have one smart contract on Ethereum that emits a message or that emits some kind of information that is basically able for a smart contract on near to listen to that and to start minting things, right?
Yeah. So.
Like one thing that is it's definitely very complex, but what you need to validate, I don't think that is the consensus. I think the thing that you need to validate is the state. You need to make sure that the state is actually this one. This is the finalized state, because this is the one you know like exactly what happened.
Yeah, but to validate the state, you have to validate the consensus. Because if you don't, you can forge another state. Like, basically, the whole point of the consensus is to agree on the state root, right? And so maybe something that I did not mention here is that you are not like on the light client here. You cannot directly listen to Ethereum. So it's relayers that are coming and bringing the information from new blocks. But the great thing is that now this time you don't have to trust the row layers. They are not like trusted like in this system. They can just not post wrong roots. For instance, with the Ethereum 2.0 consensus, they could not, like if it's validated here correctly, they cannot bring blocks that have not been signed by a majority of the nodes according to the Ethereum consensus system. So yeah, I don't know if I get your question right.
No, what I mean is that you don't need to run the consensus. You need to listen to the consensus in the sense where like you need to trust the consensus in the sense that if you need to rerun the consensus, that you would need to create a like you would need to have a lot of computation. Like
Yeah.
here it's a light node, so what you're doing is basically you're listening to the consensus. You're making sure that okay, I can actually do that because the block. This block that is actually finalized on Ethereum has the information that makes me believe that they can trust, that makes me believe that they commit. So I think that we are explaining the critical, how do you say it? And you don't rerun the consensus. It's like a lot like
You actually run the consensus. Like you cannot just listen to a node or a source because you cannot know if it lies or not. Like for instance, if I come here with a like fake block hash with like signatures that are not valid, the whole node would be actually run in the contract, and so it will verify also the signatures. Like I guess it might be different from the light clients that you run off chain, in the sense that maybe in the light clients that you run off-chain, you don't verify the whole consensus, you just listen to some trusted nodes maybe, but it's not actually the case here, because if it was the case, the row layer could forge messages. So you actually have to like run the consensus. That's why it's hard, and that's why the contracts are crazy complex. And that's why it's so hard to put in a circuit also.
But I guess if you render a BLS signature, you can aggregate like all validator signature into one signature.
For Ethereum, yes. You can do some of this. Okay, so now let's go a bit deeper on light clients, and let's try to create a light client. Let's try to create a Bitcoin to Ethereum bridge. So this has already been done on one side. So here we have Bitcoin. And you will see the problem very, very fast. I promise you. So you all know there's like $500 or $600 billion of Bitcoin that are not moving much. Wouldn't it be cool if we could have wrapped Bitcoin on Ethereum to do DeFi or crazy things with it? Well, actually, we have wrapped Bitcoin, and it's managed by a company called BitGo. So it's exactly the thing. It's even worse than MPC or TSS. It's just one company, so it's completely custodial. So you might be thinking, is there some people that have tried to validate the consensus of Bitcoin on Ethereum? Like do a light client of Bitcoin on Ethereum? So the idea is that basically if you do a transaction that like locks some Bitcoin on Ethereum, on Bitcoin, you can actually mint some wrapped Ether some wrapped Bitcoin, on Ethereum. Well, actually, a lot of people have worked on it. I think the first guy was James Prestwich, like years ago. He did a proof of concept of this. Like DC, who is working on Daimo, who was here the other day, he actually also did a proof of concept of this. So it's actually possible. And basically, the way that you validate it is that you have to run some kind of Bitcoin light node on Ethereum, right? You can do it because Ethereum is Turing complete. And the idea is that you have at some point a transaction here, and you want to validate that it has been included in Bitcoin in the light clients here. And the way you would do it, because now you don't have BLS signature and Ethereum 2.0 and all of those consensus algorithms, you have proof of work. So how do you prove proof of work in it? Well, basically you would use, maybe you won't like validate from the first block all of the blocks because that would be complex. You could do it with like recursive snarks and crazy things. There is a team at Celo that has been working on things like that. But basically the way you would do it is that you would say, okay, give me a transaction that has been included in a block and give the block hash. And then give me the next few blocks, okay? And I'm going to check that the next few blocks actually have the right difficulty that the Bitcoin network uses. So if I craft like random fake blocks on my side, the difficulty is not going to be very high. I'm going to be able to like put a fake difficulty, but like the contract here can keep track of it and know that it's not the right difficulty of the Bitcoin network. If I want to craft blocks that actually have the difficulty of the Bitcoin networks, it's going to be pretty hard to do if I don't control most of the ASICs, like or at least more than 50% or some kind of close like ratio that's mine on the Bitcoin network. So basically, the way you would do it is that you would say, okay, give me the block that includes your transaction. So we have, okay, here you have your transaction, and give me the next blocks.
So if the miner can continue mint the blocks, then they can.
If they can continue to shadow mine the blocks without revealing to the other like Bitcoin miners, they can actually craft a fake transaction, and that would be why you would need a lot of them. And basically, this is, and here is your security parameter. So if you want to be really, really sure, it's just like when exchanges, they want a certain number of confirmations before you withdraw. It's exactly the same thing. If you want to be really sure, you put 100 here, and you would have to shadow mine 100 Bitcoin blocks without telling anybody, having a lot of ASICs to do that, so a bit hard. So it would depend on the security you want. Okay, so a lot of people have been doing to do that, and it's been a long time. You can actually verify on Ethereum data from Bitcoin. It's just a bit expensive to do it. It's a bit expensive because you have to actually relay most of the Bitcoin network. I mean, either you have to relay it to be able to have it all, or you do this technique. But it's not that useful if you can only go on one side, right? Because if you really want to do a wrapped Bitcoin implementation, you have to be able to go on the other side, right? You have to be able to have a system here. So some kind of Ethereum light clients that says, okay, now you burned the wrapped Bitcoin on this side. And so now you can get back your Bitcoin here. But maybe now you see the problem, right? Bitcoin is not Turing complete. You cannot do that. You cannot put contracts. You cannot create a light client of Ethereum on Bitcoin. Bitcoin, you have Bitcoin script. Okay, it's bad. Blockstream, they don't want. Okay, new opcodes. Okay, let's not go into that debate. But you cannot like have compute basically done on Bitcoin. You cannot verify at all the consensus of Ethereum. So now we've got this design that's already been done. But that's bad because you can actually like mint some right Bitcoin and then you cannot withdraw them. Okay, is everybody up to like, am I clear here or do you have any questions? Because this is going to get into some crazy things. So.
It's like FTX. You can only deposit, you cannot.
Yeah, this is, yeah, basically. So now like, yeah.
I was thinking that there's just something I was thinking about in the last days, but I feel that potentially the future of Bitcoin will potentially be on Ethereum, where nobody will really use Bitcoin, but everybody would like want the security and like the value of Bitcoin in the sense that everybody's going to use wrapped Bitcoin, at least most of the time. And so like, do you really want to have Bitcoin on Bitcoin? So maybe wrapped Bitcoin is what like everybody will use, and everybody will use wrapped Bitcoin as Bitcoin and sell it on exchanges and stuff like that.
Oh, okay, so yeah, I think also that Bitcoin has a bright future outside of Bitcoin. If what you mean is that like people can consider what Bitcoin as the consensus, like they all believe it has value. Okay, if the social consensus turns out that way, then it can add value. But still, if you cannot bring it back to like to the Bitcoin chain, it's a bit sad. It's not really Bitcoin anymore. It's just a new kind of fork of Bitcoin that's running on Ethereum. People actually consider the wrapped Bitcoin as some kind of Bitcoin, but it's managed by BitGo. BitGo, if they want, they can just mint an arbitrary amount of it, so it's not that good. Okay, so this problem, like a lot of people have been thinking about it for a long time, because the first bridges that people actually try to do, and probably the biggest market for bridges is just bridging Bitcoin on Ethereum. And here you cannot really do ZK in any way, right? Because, okay, you're going to do ZK like the crazy people from Succinct Labs or from Polyhedra, that was previously called ZK Bridge. You can now validate, you have your crazy circuit that contains the whole Ethereum consensus. You can validate it on a chain in the succinct way, but you have nothing to validate here. You cannot have smart contracts or a verifier, even if it's succinct. It's actually like the guys from Chainway that are working on a Bitcoin rollup that went here the other day and made a little workshop. It's actually similar to the problems they are having. So they use a bridge that's a bit trusted and which you have majority abstention. Okay, it's quite bad, but it's hard to do the things I'm going to explain just right here. And so Leona, that was here the other day talking about Intmax. He has been working on some crazy designs using something called witness encryption. So who here has heard about witness encryption? He has. Wow.
You do.
Okay, so basically, this is where I'm not going to go that deep into the math, but I'll try to give a brief intuition of the math. Okay, but basically witness encryption is, I don't think it's ever been used in production or in any system. It's been studied for like a few years. So I think like the papers that really introduced it is one from like GAG from 2013, but there's been new schemes now. Some schemes are based on lattice cryptography, some schemes are based on like other systems. And basically the idea of witness encryption is to be able to say, if you know the solution to this problem, you will be able to decrypt this message. So it's kind of like ZK, it's not really like ZK. ZK is like if you know the solution to this problem, to an arbitrary circuit, to a circuit that we can do, you can like have a verifier that verifies it and outputs 0 or 1. Witness encryption is kind of like the same thing, but in the end, you can decrypt a message or not decrypt it if you don't have a witness. So, like if you go to the article by Leona, I will write his the name of the article here. It's just trustless Bitcoin bridge creation with witness encryption. You will like find quite easily it on the internet. And basically, the idea of witness encryption is that you've got two steps. So the first, wow, oh, didn't break anything. So the first is and it gives you a ciphertext. So the first step is the encryption. It takes a security parameter. It takes X, that's the X, so it's the instance. So it's basically the circuit or the problem that you want to encode. And M is the message that you want to encode. And then there is decryption, in which you take the ciphertext that's outputted here. You have a valid witness, and it returns the message M. Okay, so the first, people have been trying to do that, for instance, with Sudoku. Like if you know the solution to a Sudoku, you can actually like decrypt a message and have it. So there have been implementations that work on like basic problems, but I don't think it's ever been used like for other things like this. So as you can see, it's quite similar to ZK in some way. The main difference here is that instead of having a verifier that outputs 0 or 1 if the witness verifies the instance, now you are encrypting a message. And you can only decrypt it if you know a valid witness. So in what way is it linked to all of this? Well, you might actually guess that if you can actually do an Ethereum like consensus light client that you encrypt in kind of like in a ZK circuit, but in a witness encryption circuit, you can actually have a circuit in which if you know a valid witness, which would in this case be an Ethereum block in which you have burn transactions, you can actually get back your Bitcoin here. And how would you do it? Well, the witness encryption would reveal to you the private key because you have no way of doing better. So it's not like contract. So it will reveal the private key of the Bitcoins on the Bitcoin blockchain. Okay, it's a bit confusing, or is it like, is the intuition here? Yeah? Okay, very good questions. I'm going to explain it a little bit better. Do you have a question, Ayush?
When you transfer Bitcoin to Ethereum, do you put it to one particular address or to like every deposit is a different address on Bitcoin?
You would put it in a different address, and then like
If that address would be
yeah, basically the trick is that you will put it in an address that nobody in practice knows the private key of, but the private key is encrypted with witness encryption, and then when you want to go back, you will actually get the private key, and it uses a trick to be able to be sure that nobody knows the private key of this lock, which is that in Bitcoin you cannot do smart contract, but you can still do n out of m out of n or n out of n multisigs using the opcode multisig. And you can like do a kind of Gross16 like setup ceremony in which you've got many people that actually create a multisig and that prove, I'm explaining the whole thing here, but let's hope that is clear, that prove that they generated like the private key, but it's with a kind of MPC setup, so it's 1 out of n. So basically all of them have to cheat if they want to like forge transactions. And they prove that they generated their secret according to the system that makes witness encryption works. And basically what you end up with is a system in which you have to have all of the participants of the ceremony cheat if they want to send another transaction. Nobody actually knows the private key except the person that ends up knowing the valid witness and that can withdraw on the L1. Okay, I know it's a bit messy. It doesn't seem clear for... No, it's...
How the user get the private key? Is that the get from the contract, or how you get that?
Okay, maybe I'll do I'll do a little diagram. So
yeah, that's my
no,
that's my question.
no, it's not on chain. Basically, you would. I mean, okay, is it on chain?
Yeah,
No,
it sounds like keep that private.
If it was on chain, then it's just like the fastest guy that takes it.
yeah, but it's not like on chain.
For the n-1 people?
And my
In your trusted setup, so you say, it's one, and then you have an n number of people. Or
Yeah.
number of, so for the n,
So-
myself and who else?
So basically, those n people would be. It's kind of like a trusted setup ceremony for Gross16 or other like ZK scheme that need it. So basically, you would have anybody that would run the thing, just like Zcash, the guys from Zcash did when they deployed it on the first time. Basically, it could be anybody that runs the program correctly, and who, okay, I'm not that familiar with all of the process, but basically that runs a setup that will generate like a private key, and that contributes to the final thing to generate the addresses that will be used as deposit addresses for the Bitcoins and on the Bitcoin network. And so basically those n people can be whoever participated at the ceremony. It can be 1,000 different people. And if it's 1,000 different people, it's kind of like a Gross16 setup ceremony. Anybody can you can just run it and add your own like contribution to the ceremony. Somebody else can run it. And if you've got 1,000 people, you actually have to have 1,000 of them all of them to collude if they want to send a transaction and to get the private key back. The only other way to get the private key is with the witness encryption thing.
And in this case, because Gross16 is circuit specific, so that means that you probably have like maybe even a market thing that these people would constantly run this trust setup.
So it's not Gross16 that you're using. It's like I'm comparing it to Gross16 because it's the same kind of setup, but it's not Gross16. It's a crazy witness encryption thing.
What I'm trying to say is, like, does that mean that for every bridge that you do, you have
now you can do one big and then generate an arbitrary number of deposit transactions, and then people can bridge using them. But you have one drawback is that you cannot, for instance, bridge 2 Bitcoin and then do one, do one back and then one back. You cannot have this because you don't have programmability. Either you have the private key or not. So if you bridge like 2 Bitcoins in this direction, you will only be able to withdraw 2 Bitcoins by proving that you have burned the wrapped Bitcoin and included in a transaction, and all of this is in the big circuit that's used by witness encryption. Okay, okay, I know how witness encryption works is not clear. Don't worry, it's not clear for me either. But is it like, is the intuition of the thing here? Basically, the only thing to understand is that if you want to do a very secure bridge, you want to have light clients on both sides that validate the consensus. You cannot do that on Bitcoin. So you have to have kind of ZK magic, but you cannot do ZK either because you cannot put a verifier. And so you use this new primitive witness encryption that's just like ZK, but it actually allows you to decipher a message. And if you want the full flow, basically the first thing that you would do is, so you would like record, so the very first thing that would be done is the ceremony that we just talked about, and in which you would like create a lot of Bitcoin deposit addresses. Then as someone who wants to bridge, you would send some Bitcoin to this address. Then on the smart contract that's on Ethereum, you would put your home address, you would put the address in which you deposited. Then here with the classic Bitcoin Lite client, just like we talked about, that verifies the Bitcoin consensus. You can do it at Ethereum, it's Turing complete. You can verify that you actually deposited it in the contract here. So now nobody can touch this Bitcoin except if all of the people collude, or if you know a witness, a valid witness to the witness encryption thing. So now you have your wrapped Bitcoin, you are very happy. You can do crazy DeFi with it. And then if you want to go back, remember you cannot go back partially. You have to withdraw all of them at the same time. So let's see. You burn the wrapped Bitcoin. So you send them to address 0000 or address dead. And then that's where the magic happens. You basically prove in the circuit, the witness encryption circuit, that you know of a valid state root that has actually been validated by the Ethereum consensus, that contains your transaction that burns them. And if the thing works well, you have now, if you have a valid witness, this, and you have the ciphertext, which is the thing that was done with the setup that we talked about. Now you have the private key and you can just spend the funds on Bitcoin. Yes?
You mentioned that you have to withdraw all of the Bitcoin.
Yes.
Does that mean like every deposit transaction will be like a different Bitcoin, like a different
yes, because you cannot, my God, you cannot do one bridge contract just like on Ethereum because you don't have logic. If you give the private key, someone can remove it all. So you have to have different, it's really atomic. You have to have different like deposit addresses for each one. But the great thing is that with one trusted setup, it's not really called a trusted setup, but it's an n out of n multisig that you generate using this process. You can generate a big number of deposit addresses. So you can know it.
But let's say I deposit 5 BTC, I get 5 WBTC on Ethereum. I do some DeFi, now I have like 2 BTC left. Can I withdraw this?
No, you have to withdraw 5 of them.
5 BTC or can I?
Oh no, it can be different. Wrap BTC, but you have to have 5 to withdraw. But maybe after. Okay, maybe you can go into some UX implementations, for instance, having a marketplace of people that like sell the witnesses or some crazy things like this to be able to make it more liquid. In practice, if anybody were to implement this, you would have marketplaces that are really easy to swap arbitrary amounts. So just like in... Sorry?
Can be put in an AMM, these witnesses, to create a market? Because you need to add exactly the same number, right?
Okay, so like can you, okay, so you cannot put like the witnesses in an AMM, but you can make a marketplace. It's actually been done by Pierre XYZ from OXPark. Put a marketplace of, like, he's done a marketplace of gross 16 proofs in which, like, you can actually sell them. And so you would have to do a marketplace of witness encryption proof. My God, witness encryption, nobody knows if it's really implementable that well today. Doing a marketplace of this seems complex, but I think the most easy answer would just be to have like arbitrageurs that are here and sell you directly like peer-to-peer, some wrap bitcoins for some bitcoins, or you just go on an exchange or whatever in practice, and it would be easier than like the whole thing.
What's the implementation happening today? Like, what's the biggest roadblock?
I'll tell you. Okay, I'll tell you just after.
Do you have more information about the Lambda and X there?
About the Lambda? Yeah.
I was out of my mind, you know, while we were giving the elaboration.
Okay. So Lambda is a security parameter.
Yeah.
It's also the case in, it's also like everywhere in ZK, for instance. And it's basically a security parameter that's going to define how secure the system is.
So that Lambda. But
Yeah.
What about X there?
So X is the instance. Most of the times we don't call it X in ZK, we call it like I. But here in witness encryption, it's called X. And it's basically the whole circuit that you're trying to validate. The whole. So in this case, it will be a crazy big circuit that implements the Ethereum consensus. So that's the problem basically. If let's take a simpler example of the Sudoku grid. This is a security parameter that defines how secure it is. This would be the Sudoku grid, but defined as a circuit. This would be the message I want to encrypt.
In this case, it's
Like, like my, I don't know, my password to an account. And then if you have a valid witness, which is the right numbers that validate the instance, so you have a solution to the Sudoku circuit, and you get the ciphertext, then you can decrypt my password, which in this case is a Bitcoin private key. Is it? Okay. Basically, it's.
still hard to imagine. Yeah, but I'm
Yeah,
trying
it's hard to imagine because, like, just like ZK is quite hard to grasp at the start. So yeah, you were asking about like more detail about how witness encryption works, right? No? What was your question again?
Why isn't this being implemented?
Well, why isn't it implemented right now? Okay, so basically, Leona, if you are interested in this, read this article. It's very good. He explained better than me. Basically, he cites like the different best approaches right now, or like the approaches that people think that are interesting and that could be promising for witness encryption. And so basically, some are based on lattice cryptography. So lattice cryptography is this idea of you have like n-dimensional spaces that are really big, just like lattices. So you have points on them, and you have problems like finding the shortest vector or finding one point that's the closest to another. And it seems easy if you draw a grid, but if you do an n-dimensional lattice, it becomes an NP problem that's absolutely crazy and quantum resistant. Okay, this was a very, very like summarized version of lattice cryptography, but just my intuition of it. And the one he actually goes more into describing is called ADP. So ADP is affine determinant programs, and basically I don't understand it very well, but rapid, very brief intuition of how it works. Basically, it's kind of like an inner product argument. So there are also like witness encryption schemes based on inner product, and basically the idea is that you can decrypt the message only if the inner product ends up being 0 or 1, like a specific value. And it's kind of like inner product argument in ZK, but you can like decipher a value with it. ADP is a bit like the same idea. You've got basically, okay, I can write it down, but I'm going to give you the intuition in really fast. Basically, you've got this big matrix that is a sum of a lot of different matrices, and you're going, and it's a matrix that, like, it's actually a function that takes as input the witness you're giving it, and you can actually only decrypt the message if the determinant of the matrix at the end is 0. And so there is like some noise techniques and everything to make it hard to brute force. And actually, only with a valid witness, you will be able to have an input matrix that actually fits with all of the other matrices, so that when you sum all of them up together with like also coefficients that are in it, you make a kind of big sum. Kind of the same way that when you use like inner product arguments, you do a big product. Then you will be able to like decipher the message. That's also encrypted in the matrix, and then you can like withdraw your Bitcoin and be happy on Bitcoin layer 1.
And this can only be done with lattice cryptography.
No. So ADP is not lattice cryptography. It's different. There are multiple approaches like ADP lattices, and also others are inner product encryption and multilinear maps. So all of those are not lattices. Inner product encryption is quite close to functional encryption. Functional encryption is another primitive that allows you, if you know a witness, to be able to compute some function over encrypted values. It's quite close to witness encryption, but it would be other use cases. Like for instance, we've got private encrypted values of like a database with private data of people, and you have to have a valid private key to be able to compute some functions over them, but you get zero other knowledge about the data or about other functions that you could compute on it. And it's very related to witness encryption.
That's FHE, right? Fully homomorphic encryption.
Okay, I don't think that's FHE, because basically in FHE I think that's close to FHE but different, because the difference is that you need to know like a private key or a witness to be able to compute some function. FHE is more like you will make an encrypted version of the data, then it's homomorphic, so you can like do operations on it, but you don't necessarily have to have some private key to be able to, or some specific secret to be able to do those homomorphic, like those computation on the encrypted data. Don't know if it's clear, but like all of those concepts are related. Okay. Yes. How do you get your private key? That's the magic of this. Unfortunately, I cannot explain it that much. I have some formulas.
I understood that it's like encrypted, and that like by giving the witness, you can like actually get it.
Yeah.
How do you like physically get it? How do I get access to the private key and then import it into my data?
Okay. Okay. So first, if I'm not mistaken, it's a completely off-chain process that only happens on your side. Because basically, so let's see, I don't want to say like things that are not true. So let's see, like here, yeah, so basically it's off-chain. Like you cannot even put smart contracts on this in any way. So it's just like you have this ciphertext that I guess anybody can download, and this process, and if you have a valid witness, you can get it. So actually, it would be a process that you run completely like on your browser or on your computer, and it would like output the private key that you can then use, not in MetaMask because no Bitcoin on MetaMask, but on like a Bitcoin wallet.
Then
I'm curious about like just the delivery of the private key, because like that's a pretty complex topic in the sense that you need to make sure, for example, like, if you're not the only one that has access to the computation, and it's not like purely local, in the sense that you need to request some data from the network to be able to submit a witness, and it means that like they potentially also have the challenge, so they have access to the challenge. So if you submit the witness, then potentially they
Okay, I see. Yeah.
They see the witness, right? And so they can submit it and get access to your private key.
Yeah, I guess just like you would like put, for instance, commit your address in like I don't know, a Tornado Cache proof to be sure that you are the one withdrawing. I guess you can do a pretty similar system in which even if somebody else gets, okay, either you like pre-commit your address and you need it actually to be able to withdraw, either you don't pre-commit it, but then the Bitcoin can only be withdrawn to your address. It's not possible because you have to have the, sorry, I'm thinking, like the private key gives all of the power of the Bitcoin. So I guess it's something like you pre-commit your address somewhere and only you can yeah, it's a good question. It must be somewhere in the paper, I guess. You must be talking about it. I guess that, yeah, I don't know precisely actually.
You can do it offline, right? Like you have the cipher text, you calculate the witness, you do it offline, you have private key, then
You can do it offline, but the node actually sees your transaction that's validated here when you burn, and so somebody else could come and see the transaction, and in theory they can have the same witness.
Okay.
So I don't know about this
Can
part.
user just download that CT and do the decryption for in your browser? So is that totally offline?
Good question.
I guess this could be offline. Right now it's not implemented, but
Yeah, because you cannot get a private key from the node, right? I really know that.
you cannot get it from.
the network.
Yeah, no, you cannot
Yeah,
get it.
yeah.
You would do all of this like in your browser or on
Yeah.
your computer. Yeah.
And but networks need to make sure that you already burn your token.
Yeah.
So I think this kind of data or this kind of proof you need to get from the node. Otherwise,
Oh yeah,
you cannot make sure.
yeah, you would get the block from the node, but then you would compute the witness encryption scheme locally. But yeah, the blocks, the public data, you get it from the node, and so you can get all of the data that allows you to prove that you have in one of the state routes you have your transaction.
I guess you might also have to prove that you have the key that made that transaction, like in the Ethereum side. That's the only I can think of.
Yeah, exactly, and that's the way you can like make sure you are the one doing it. Just have to verify like a signature on your side, or yeah. Yeah, it would need to be in the witness encryption circuit,
Yeah.
with like aside from the consensus.
Yeah. Aside from testing the transaction is in the consensus or whatever, you also tell you have the private key who made that transaction.
Yeah. So basically, I've already like been quite long. I'm not going to continue further, but just a very quick thing. Basically, the main reason why it's hard, and to also answer your question, is that right now witness encryption schemes are quite inefficient. Each time you add a constraint, you add a lot of complexity. The current schemes, some of them are considered secure, but hard to implement. Probably we are in the same place as we were in ZK like 5 years ago or something. And so, so it's a bit hard. Like it's already hard to do ZK circuits with the Ethereum consensus, but it's even harder to do it with witness encryption. So the idea that Leona has been thinking more about recently is just doing a Bitcoin side chain that uses proof of work, and this is a lot easier. Proof of work is a lot easier, lot smaller circuit to implement than the whole Ethereum consensus, and you could even do merge mining with the Bitcoin. If you know what merge mining is, basically it's you do a side chain but use the same like mining algorithm. So you actually are profiting, like you are getting all of the security from Bitcoin because you are just kind of stealing their mining. Not really stealing, but you are implementing the same mechanism. It was the time when a lot of Bitcoin forks were like implemented, like in 2015 and 16 and everything. People did merge mining so that they could inherit the security of Bitcoin. And so basically, using this kind of thing, you could do a layer 2 on Bitcoin that's Turing complete, so like EVM, and that would be that would have a trustless Bitcoin bridge. And it's actually not, maybe it could be feasible. It's not as hard as validating the whole Ethereum consensus. And the guys from Chainway, if they did that, that would be a real breakthrough. the guys that work on BitVM. That would also be a real breakthrough, probably a lot better than BitVM because the design of BitVM has several drawbacks. And like in my opinion, the opinion of Leona also, it would be like the best way to do an L2 on Bitcoin because you basically inherit like most of its security. The only thing, the only like additional trust assumption is that witness encryption works well, which actually right now is like still a bit unsure. Okay. Yeah.
Maybe it's like a off a tangent, but like, you know, like what about like all those development on like scripted stuff like? How we've talked about like you know how they talk about doing smart contracts on Bitcoin SV. Like, would that ever help with the development of this?
On Bitcoin SV?
Yeah, have you heard of like?
Yeah.
Those. They have some sort of early prototype of doing smart contracts on.
Yeah, I don't know much about Bitcoin SV. I guess you could do things on it, but it's not recognized by a lot of people.
Yeah.
So, yeah. But I know there are forks of Bitcoin that support more things than just Bitcoin script. Okay. Thank you very much.
I can go. Mine will be very short.